Welcome to Easy Elim Learning Simplified. My name is Ruth, and today we are going to be learning on Form 3 Chemistry, and our topic for today is gas laws. So today we are going to be looking at the combined gas law, and then we are going to look at the standard conditions and then do a few questions. So both temperature and pressure changes in a gas cause the volume to change. So the volume of gases are always compared under the same conditions of temperature and pressure. So you see us mentioning the statement STP. STP means standard temperature and pressure. So at standard temperature and pressure, the temperature is at 273 kelvins, which is the same as 0 degrees Celsius, and the pressure is at 760 millimeters per mercury, that is the same as 1 atmosphere. And then RTP refers to as room temperature and pressure, and this is at a temperature of 25 degrees Celsius or 298 Kelvin, and a pressure of also 1 atmospheres or 760 mmHg. So these are the standard conditions we are going to be using mostly when we are looking at the calculations of the combined gas law. So the standard pressure is the atmospheric pressure, and it is equal to about those pascals, Newton meter squared, and then 760 millimeter mercury, and then 776 centimeter mercury, and then 1 atmosphere. You'll notice that we are going to be using millimeter mercury and also 1 atmosphere in our calculations. So a general gas law relates to the change in the pressure, volume, and absolute temperature. It can be derived from the three gas law. We have pressure law that we didn't discuss, but we are going to combine the Charles law and Boyle's law that we discussed in our previous lessons. So the law that we form by combining these different laws is what we call the combined gas law. So we said that the Charles law relates volume to temperature, and we said for Charles law, the volume is directly proportional to temperature. If we introduce the constant, we remove the sign of proportionality, it becomes V is equals to KT. If we want to remove the constant or allow the constant to remain in one side, it will become V over T is equals to constant. As for the Boyle's law, it was a relationship between pressure and volume. We said that volume is inversely proportional to pressure. If we introduce the constant, we remove the sign of proportionality, it becomes V is equals to Kp over P. And then if we want to be left with constant one side, it becomes constant is equals to V over P, or V times P. So it becomes constant is equals to PV. So those are the expressions of the Charles law and Boyle's law. So if we multiply the constant together, if you combine the two laws, you multiply both constant, you notice when you combine those two laws, you're going to get PV over T. That is going to be the combination. Therefore, if we pick like a variation of a gas that has a certain volume and pressure at a certain temperature, and another gas, we can call it 2, which has a certain volume and a certain pressure at a certain temperature. So our law is going to be P1, V1 is equals to T1, which is the same as P2 or V2 is equals to T2. So this is what we usually refer to as the ideal gas equation. The P1 V1 over T1 is equals to P2 V2 T2. Remember, this ideal equation can be written in different ways depending on what you have been given. You can decide to cross multiply this equation, and if you cross multiply, you're going to get T2 P1 V1 is equals to T1 P2 V2. So depending on the value you want to be left with one side or the value that you're looking for, you can be able to do the math and get the values that you want. So when we do a few assumptions of the gas law, we usually explain that the gas law using kinetic theory. We talk about the size of the molecules and the intermolecular forces. So when we are explaining in regards to the kinetic theory, we usually assume these values to be negligible. So we are going to differentiate between a real gas and an ideal gas. So a real gas is defined as a gas that does not obey any gas laws at all standard pressure and temperature conditions. So real gases do not obey these laws. They have velocity, volume, and mass. It occupies space and the molecules have interactions. So if you look at a normal real gas, we have said when you look at the gas laws in regards to kinetic theory, we look at the size of the molecules and the intermolecular forces. So for a real gas, you notice it occupies a certain space and the molecules usually have interactions. So real gases have molecules with definite volumes and therefore an ideal of zero volume or zero pressure is not real. So real gases get liquefied before zero volume is reached. So for an ideal gas, which is completely opposite of the real gas, is defined as a gas that obeys gas laws at all conditions of pressure and temperature. It has velocity and mass, but they do not have volume. When compared to the total volume of the gas, the volume occupied by the gas is negligible. It does not condense and does not have a triple point. So an ideal gas is a theoretical gas composed of many randomly moving particles that are not subject to interparticle interactions. So you see, this is different from the real gas where the molecules have interactions or there are some forces in between the particles. But for an ideal gas, particles are moving, yes, but they do not have any interactions at all. So let's look at a few examples of calculations in regards and applications in regards to the combined gas law. And then we are going to also look at what we have discussed. So a mass of 1,200 centimeters cubed of oxygen at 27 degrees Celsius and a pressure of 1.2 atmosphere is compressed until its volume is 600 centimeters cubed and its pressure is 3 atmospheres. Calculate the temperature of the gas after compression in degrees Celsius. So the first step is to identify the values that we have been given or to identify the pressure, temperature, and the volume that you have been given. So going back to the question, we have been told a mass of 1,200 centimeters cubed. So we'll call this volume 1 because it's our first volume. It's 1,200 centimeters cubed of oxygen at 27 degrees Celsius. So our first temperature will be 27 degrees Celsius. Remember, we said whenever we are doing any calculations, usually we said that we have to convert the temperatures from degrees to Kelvin. So this is going when you add 273, you're going to get 300 Kelvin. So we are going to use the Kelvin instead of the degrees. And then a pressure which will copy P1 is 1.2 atmospheres. And then it's compressed until its volume. So we have the second volume, which is 600 centimeters cubed, and its pressure, which will be our P2, is equals to 3 atmospheres. Calculate the temperature. So we are looking for T2, but our question has said specifically you leave your answer in degrees Celsius. So after identifying the values that you have been given in the question, the next thing you do is you write the formula of the combined gas law. So it is P1 V1 over T2 is equals to P2 V2 over, this is T1, T2. So let's input our values. Our P1 is 1.2 times our V1 is 1200 all over our T1 is 300 Kelvin is equals to our P2 is 3 atmospheres times our V2, which we do not have, and then everything V2 we have it's 600, and then everything over T2, which we do not have. So we can decide to work out values, or we just cross multiply and until we end up getting what we want. So first of all, we can work this value out. So 1.2 times 1200 divided by 300 gives us 4.8 is equals to, if you multiply 3 times 600, you get 1800 over T2. So we want to be left with 2 to one side, so we will cross multiply, which will give us 4.8 times T2 is equals to 1800. We divide by 4.8 both sides, we get our T2. Remember, it is going to be in Kelvin, so our T2 will be 1800 divided by 4.8, which gives us 375, and we said it is in Kelvin. So our question tells us that we need to leave our answer in degrees Celsius. So we are going to say 375 Kelvin. 375 subtract 273. So we are going to get 102 degrees Celsius. So that is their answer. So you've seen the way we have worked out the question using the formula. Let's do another question. A gas occupies a volume of 400 centimeters cubed. So what you're going to do a bit different from what we did in our previous question is we are going to integrate our writing with the reading. So whatever value we notice in the reading, we write them down. So in this case, our volume 1 is 400 centimeters cubed at temperature 1, which is 500 Kelvin. So it has already been converted, so we are not going to convert. And then add 1 atmospheric pressure. So P1 is going to be 1 atm. What will be the temperature of the gas when the volume and pressure of the gas is? So we have volume 2, which is 100 centimeters cubed, and pressure 2, which is 0.5 atmospheres. So we have been asked to calculate the temperature. So once again, we write the formula. So the formula is going to be P1 V1 over T1 is equals to P2 V2 over T2. So we input our values. It's going to be P1 is 1, atmosphere V1 is 400, divided by T1, which is 500, is equals to P2, which is 0.5, times V2, which is 100, divided by T2. So we can work this side first of all. We can divide 400 by 500. That's the same as 4 divided by 5, first of all, before we cross multiply. So 4 divided by 5 will be 0.8. So 0.8 is equals to 0.5 times 100. You can just do this quickly. It's going to be 50 divided by T2. So we cross multiply. So 0.8 times T2 is equals to 50. You divide both sides by 0.8. 0.8. So our T2 is 50 divided by 0.8, which will give us 62 0.5 Kelvin. Since you have not been told to convert this into degrees Celsius, you can leave your answer as it is. Let's do one last question and then we'll close the session. Form 3 students found that the mass of nitrogen gas occupies, so we have volume 1, which is 330 centimeters cubed at 280 degrees Celsius. So temperature 1 is 280 degrees Celsius. So we said you convert this to Kelvin. So 280 was going to be plus 273, which will give us 553 Kelvin. And 760 mmHg. So we have pressure 1, which is going to be 760 mmHg. And then at what temperature, so our T2 is what we are looking for, with the volume of the gas, V2 is 190 centimeters cubed, and pressure is P2 is 800 mmHg. So once again, we write the formula, it's P1 V1 over T1 is equals to P2 V2 over T2. So we input our values. P1 is 760, our V1 is 330, and then our T1 is 553 Kelvin is equals to our P2 is 800, and then our V2 is 190, and then divide by our T2, which we do not have. So once again, we do the calculation in one side. So we are going to do 760 times 330 divided by 553, which will give us 453.53, which is equals to 800 times 190 divided by T2. So 800 times 190 will give us 152,000, and then this is divided by T2. If you cross multiply, you get 453.53. T2 is equals to 152,000. If you divide by 453.53, divide by 453 by 53, so you get your T2 as 335.15. That is our T2, and this is in Kelvin. If you haven't been told to convert, do not convert. So that brings us to the end. It does not mean necessarily you can just be given to look for the temperature. The questions that we are working was just for temperature. But remember, using the formula we just did previously, P1 V1 T2 is equals to P2 V2 T1, can be used to get any value that you have been given. Remember, when we are calculating our temperatures, you have to convert them to Kelvin. Leave your answer in Kelvin unless you have been told otherwise, because those are the ones that are required for the calculations. So see you in the next session when we look at diffusion.